Now we turn to what recursion really is. Let's break a recursive function into its parts. A recursive function has exactly two parts plus one duty. The first part is the base case. It answers directly with no further call. In factorial, the base case is, if n is 0, return 1. The second part is the recursive case. It calls the same function on a smaller input, then uses the answer. In factorial, that is n times factorial of n minus 1. Before we go on, read the precondition. Factorial needs n to be 0 or more. It also needs n small enough that the answer fits in a long, which is about 20 on a 64-bit machine. Signed overflow in C is undefined behavior, not just a wrong number. Because factorial is defined only for non-negative n, the base case is n is equal to 0, and every recursive call steps down toward it. Now the one duty. It is called progress, and it is the rule that makes the recursion stop. The value you pass to the recursive call must move strictly closer to the base case every time. With no progress, the recursion never stops, even if the base case looks correct. You may think a base case only has to be correct. It also has to be reachable. A perfect check for n is equal to 0 does nothing if n never reaches 0. A missing base case and an unreachable base case are the same failure. Endless calls, then a crash. Every call, recursive or not, gets its own activation record. Think of it as a private block of memory for that one call. The figure shows one record. It holds three things: the call's parameters, its local variables, and the return address, which is where to continue in the caller after the call returns. There is one activation record per call, not per function. So factorial of 3 and factorial of 2 are different calls. They get different frames. A frame is created when the call starts and destroyed when it returns. This is the same mechanism Chapter 6 introduced for ordinary function calls. Recursion adds nothing new here.